Welcome, future AI champions. So, if you're gearing up for the International Olympiad of Artificial Intelligence, consider this explainer your ultimate study guide. We're going to completely master the most absolutely crucial method for evaluating machine learning algorithms. We are talking about cross-validation. Seriously, this is the exact secret weapon that separates the total novices from the true grandmasters. So lock in, focus up, and let's conquer this.
Okay, let's dive into this. The real-world stakes of picking the right algorithm are literally massive. You know, in machine learning, it's not just about writing clever code. It's about making decisions that can actually save lives. We've got mountains of data, we've got an arsenal of algorithms, but if we choose the wrong method, our entire AI model totally falls apart the second it faces reality. We need a completely foolproof way to know exactly which method will perform the absolute best. Let's start with our data, basically our foundation. Imagine we're building a medical AI. We've collected all these physiological variables, things like whether a patient has chest pain or if they have really good blood circulation. Our ultimate goal is to use these variables to accurately predict if a brand new patient has heart disease or not. Now keep this in mind for your exam. Medical data is almost always highly imbalanced, usually have way fewer people with the disease than without. We measure their variables, feed them into the machine, and we need a rock-solid prediction.
But here is the massive core conflict you're going to face. Which weapon do you actually choose from your arsenal? First, we literally have to decide which machine learning method is best for this specific medical data. I mean, we could use logistic regression. Or maybe k-nearest neighbors, or perhaps support vector machines. There are just so many competing methods out there. How do we possibly decide which one to trust with our patients' lives?
Now, what's really interesting about this is how we decode the essential machine learning lingo to figure out who wins. We actually have to do two completely distinct things with our collected data. First, we estimate the parameters for our methods. Like, if we use logistic regression, we have to use some data to estimate the actual shape of its curve. In the ML world, estimating those parameters is called training the algorithm. Then, we have to actually evaluate how well that method categorizes totally new data. Finding out if that curve actually does a good job, that's called testing the algorithm. Train, then test. Two completely distinct steps.
100%. Listen, let me be incredibly, absolutely clear. If you suggest using 100% of your data to train your algorithm on your AI Olympiad exam, it is game over. You will fail that question. It is a terrible, catastrophic approach. Why? Because if you use all of your data to train the algorithm, you have absolutely zero data left to test the method. Reusing the exact same data for both training and testing is just a massive illusion. We desperately need to know how the method performs on totally unseen information.
So clearly we need a better strategy. A slightly better idea is the classic 75-25 split. We basically take our giant block of data and slice it up. We use the first 75% of the data exclusively for training our algorithms. Then we lock that away and bring in the remaining 25%, our test chunk. We can then compare logistic regression, k-nearest neighbors, and support vector machines by seeing exactly how well each one categorizes that specific 25% test block.
But wait, we have a massive blind spot here. How do we know which 25% of the data is the absolute best block for testing? I mean, what if we use the first 25% of the data instead of the last? What if the absolute perfect test block is sitting somewhere right in the middle? By just picking one random 25% block, we might accidentally be testing on the absolute easiest patients or the absolute hardest ones. Our entire evaluation could be totally skewed by pure random chance.
And this brilliantly illustrates the ultimate solution, cross-validation. Instead of worrying about which single block is best, we just use them all. Imagine dividing the data into 4 blocks. Step 1, we use the first 3 blocks to train and the last block to test, tracking how it does. Step 2, we rotate. We use a completely different block for testing and the other 3 for training, tracking the performance again. Step 3, we just keep rotating until every single block has been used as a test block exactly once. Step 4, we summarize the final results across all those rotations. Absolutely no data is wasted and no test block is left up to random chance.
By forcing our algorithms to literally run through this gauntlet, rotating through every single block of data, the true champion finally emerges. In our medical scenario, we look at the summarized results and find out who performed the absolute best across all the rotated test blocks. And the winner is support vector machines. Since SVM did the absolute best job classifying the test datasets across every single rotation, we declare it our chosen method with total 100% confidence.
Bam! Just like that, the math literally proves which method dominates. No guessing, no random splits, just rigorous, unbeatable testing, clicking perfectly into place. By dividing the data into 4 blocks and rotating them, we just performed what the pros call fourfold cross-validation.
Now, if you really want to flex your knowledge to those AI Olympiad graders, you need to know that the number of blocks we use is actually totally arbitrary. We can push this to the absolute limit. What if we made every single patient their own block? That extreme scenario is called leave one out cross-validation, or LOCV. If you have 500 patients, you train the model on 499 of them and test it on the one left out, rotating exactly 500 times. Now, the graders will want to know why we do this. Well, it deeply minimizes bias, but it comes with really high variance and a massive computational cost.
Let's move to and see how this builds into industry standards. While leaving one out is a super cool extreme, the magic number you will see literally everywhere in the field, and the one you should totally default to on your exams, is 10. It is highly common to divide the data into exactly 10 blocks. This is because 10-fold cross-validation often provides the optimal bias-variance trade-off, giving you the most reliable estimate of your model's true accuracy. Oh, and for that imbalanced medical data we mentioned earlier, you'd specifically use stratified k-fold cross-validation, which ensures the proportion of positive and negative cases remains perfectly consistent across all 10 folds.
Double bam! That is the gold standard right there. 10-fold cross-validation. It provides the absolute perfect balance. You get a highly accurate measure of your algorithm's real-world performance without grinding your computer's processors to literal dust like the leave-one-out method might on massive datasets.
So, the crucial point is that cross-validation isn't just for picking between entirely different methods like SVM or logistic regression. It perfectly solves another massive headache, finding your hyperparameters. Some algorithms, like ridge regression, rely on variables that just aren't learned from the data. They actually have to be set in advance, and we do not like guessing in AI. So we can actually use 10-fold cross-validation to systematically test out a bunch of different values, rotating through the data to scientifically find the absolute best setting for those tricky hyperparameters.
Tiny bam. And there it is, we just totally conquered hyperparameter tuning. That is the true beauty of cross-validation. It's literally the ultimate utility tool in your machine learning toolkit. It ensures that every single decision you make, from picking the grand algorithm all the way down to the tiniest hyperparameter, is validated by hard, unyielding data.
Which brings us to the ultimate reality check. Without cross-validation, models are essentially totally untested on true, rigorously varied, unseen data. If an AI just relies on a naive, static 75-25 split, it is intensely vulnerable to massive blind spots. So, as you prepare to literally build the future, I want to leave you with this intense question. How many algorithms dictating your daily life right now, your credit scores, your medical diagnostics, your social feeds, are hiding fatal flaws behind a naive 75-25 split? Demand better testing. Demand cross-validation. Best of absolutely everything on the International Olympiad of Artificial Intelligence. Go ace that exam.